Hi, I am Shubhayan Sarkar from Center for Theoretical Physics at the Polish Academy of Sciences. So first, I would like to thank the Q Science Days committee to give me a chance to present my work. So today I will be presenting on the topic universal notion of classicality based on ontological framework. So let's begin. So first, what I would like to describe is what I consider the most natural picture that any physical event can be modeled up into. So there is a system, uh, you can call it a system, a state, or a preparation. It goes through an input, it interacts with a process, and then there is an output. So this is known as operational picture of any physical theory. So using this operational picture, you can uh, understand any statistics which is generated by any physical experiment. But however, what it lacks, this picture is uh, it's not good for predicting what future experiments might give us, or like it lacks also is a deeper understanding what my physical reality might be. So for this, in quantum foundations, what we describe is known as the ontological picture. So what you assume is that there are some states of reality, or you might have seen this before as hidden variable. So the idea is similar. So there are these physical states of reality, and there is a any system is nothing but a probability distribution over these physical states of reality. So these states of reality goes through the input, interacts with the process, and there is a change in this distribution. So in general, you might not be able to have access to these physical states of reality, but what you measure is this distribution. So just for a comparison, so any preparation or a system or a state in the operational picture is known as is denoted by P. In the ontological picture, it is denoted by mu, which is like a probability distribution of uh, the of lambda given some preparation P. And evolution, transformation, or dynamics is denoted by T in the operational picture, and in the ontological picture, it's like a mapping from the hidden variable space to the hidden variable space given the transformation T. And the third important point is to understand what measurements are. So given the outcome K of some measurement M, uh, in the ontological picture, this is represented as the response function, which is the probability of obtaining outcome K given the measurement M given the physical state of reality lambda. So in an experiment, what you observe is the set of statistics, which is like the probability of obtaining outcome K given the measurement M for a system P which underwent a transformation T. So in the ontological picture, since you in general you might not have access to these states of reality, you just average it over all the physical states of reality. And in general, it can be continuous, so you have an integral here. Just for a recap, in quantum theory, this operational probabilities is calculated using the Born rule, which is like uh, so where this rho represents the density matrices, which is a representation of this preparation. This U is nothing but the unitary matrices, which is a representation of this evolution, and these MKs are like positive matrices, which are like which denotes the outcome kth outcome of measurement M. Okay, so now what is a notion of classicality? So the basic motivation of finding a notion of classicality is to understand how quantum theory is different from classical theory. So for this, first step is to realize what constraints any classical theory must have. So we set up some assumptions which are imposed on these ontological uh, states of reality. And since if you remember, if these are like theory independent, so you have some set of assumptions, you impose it on the ontological states, and then you have like a theory which so you have a theory, and if classical theory satisfy this, then so it's a good notion of classicality. So and any better notions of classicality captures greater amount of quantumness. Okay, So for example, so let's take the most famous notion of classicality, which was suggested way back in 1964 by John Bell. So which is now known as Bell's local causality. So there, as in there is Alice, there is Bob, there is a preparation device. They receive two systems and they perform some local operations on their lab, which is like independent of each other, and they just obtain the joint probabilities, which is noted here by this quantity. So now what Bell's local causality tells us that any such joint probability must have such kind of description, which is true for any classical theory. However, what John Bell proves is that quantum theory actually violates such assumption. So now we'll move on to our work. So what we find a new novel notion of classicality, which is termed as universal classicality. So this universal classicality is based on two assumptions. So the first one is the no overlap, or that observed pure states are actually states of reality. So what it means that if two preparations P1 and P1 generate pure states, then the respective ontic distributions do not overlap. The next assumption is strong duality, or measurements do not change the system but just observe the system. So, so just to understand how this actually uh, means classical theories. So let's say that we take the example of classical Hamiltonian dynamics. So there, any state is actually nothing is represented like the position and the momentum of the system. So now you know that you can actually measure the position and the momentum. So what it means that position and momentum are actually physical states of reality, and any measurement that you do on to observe the system doesn't actually change the position or the momentum of the system, but just gives you the information of the state of the system. So in those ways, so these assumptions are quite justified for any classical theory. So now we construct an operational task uh, to see how quantum theory can violate this set of assumptions. So for this, we have an Alice who has a preparation box and Bob who has a measurement box. So Alice prepares a system based on these two inputs, which she can choose freely, independent of Bob. She prepares the system and sends them to Bob. And Bob has now can choose two different measurements, which in general can be like n outcome measurements, and performs the measurement on this. So now we find a payoff function or a success probability, which is like a combination of the statistics that you observe from these set of experiments. So what you see, so if you note here, so this is like the probability of obtaining outcome 0 of the measurement 0 given the preparation 0. So, and it's like a combination of all such sets of like the numbers which Alice and Bob can choose. And along with this, what we require is a constraint. So even in to prove that Bell's local causality is incompatible with quantum theory, what you require is that the correlations are no signal. So similarly, we have a constraint here that Bob's measurements are rank 1 measurements. So what it means is that if for any measurement, if preparations P and P prime give some outcome with certainty, then P and P prime are not distinguishable, or you cannot, there is no way to tell that P and P prime are actually different. So what we prove is that for any theory which assumes no overlap and strong duality, then the success probability is actually bounded by, sorry, 0.75. So what it means that using classical strategies in such a scenario, I can never go beyond 0.75. So, and then there exists a quantum realization which can actually give you 0.85. So which involves that Alice prepares a state which is plus in the two-dimensional Hilbert space, and the other state is like in the 0 state. And the measurements performed by Bob are like a convex combination of like Pauli Z and Pauli X matrices. Okay. And next, we prove that the notion of universal classicality implies all the previously known notions of classicality. What it means is that if I see a violation of Bell's local causality, it is also a violation of universal classicality. But however, uh, there might be an instant where universal classicality is violated, but Bell's local causality might not. So universal classicality is a better notion of classicality than Bell's local causality, and it captures uh, a higher amount of quantumness than previously all the previously known notions of classicality. So in the concluding remarks, what I would like to say is that we first constructed a novel notion of classicality, which is termed as universal classicality, which is just based on two assumptions. Then we constructed an operational task and showed that any classical strategy you cannot go beyond 0.75. And then, interestingly, universal classicality can be violated using just a pair of qubits. Uh, so all the previously known notions of classicality required either three qubits or at least systems of dimension equal to 3. But this is the first instance that we can violate a notion of classicality using just a pair of qubits, which makes this scenario much more applicable for like practical experiments. So we also concluded that violations of all the previously known notions of classicality is a violation of universal classicality. And just for a recall, I would like to say that also this result can be understood as a no-go theorem for quantum theory. So if uh, so you cannot construct any ontological model of quantum theory or like a physical state description of quantum theory uh, which assumes like no overlap and strong duality. In future, what we would like to find is like how this affects like the boundedness of the quantum set. It might lead to like new cryptographic schemes, and what I'm presently working on is to make this scheme like fully device independent. So for reference, you can check out this paper, which is posted on arXiv, and that's all from my side. Thank you.
Thank you. Is there any question? So maybe I can ask one. You mentioned about future directions. So do you think it can be also very practical solutions? I mean, you say there can be maybe some schemas, and do you
Yeah,
expect also
so
some practical?
sure, like because as I showed you before that, so what it says is that so what this scheme says is that there are some strategies in quantum theory which can never be achieved using classical strategies. So so because this previously known notions of classicality like Bell's local causality requires actually entangled states, which is not a it's a difficult resource to produce. But here we do not even require entanglement. So you just require a pair of qubits, which is very easy to produce in a lab. And mm, I, I expect that it can always it is a better resource for like cryptographic schemes. And presently, I'm actually trying to work it out like how to make this scheme like device independent, which is like a certification for like different quantum states and measurements. So yeah.
Thank you. So Ilke has a question. She's also from PC. Does your work have implications in readout correlations in practical applications?
So what do you mean by readout correlations exactly?
For circuit applications?
So yeah, so this the task which I presented can you can also implement it like a circuit, like a quantum circuit. So sure, you can like I think it's quite possible. I haven't
Readout
worked
of
it
a
out, but I
circuit.
think it's quite possible.
Okay.